Hey guys, welcome back to Google Chem Tutoring. I'm Austin, and I'll be running through an Exam 2 review. Now, with a caveat that I'm not sure what will have changed in the future for future chem classes on Exam 2, what topics will or won't be on Exam 2, so be wary that this may or may not cover everything that you need to know for your test. As far as fall 2021 goes, this is relatively accurate. But it is relatively concise and brief. So there may be like a couple other concepts that we're not going to directly cover, but that you'll still need to know in a little bit of detail. And so just be wary of that. And I'm using this review from I've made this review on my own. These are my own questions. And so you won't find these really anywhere else. But we'll be going through these, and they're mostly practice. And the idea behind this is I'd like you to look. I'm going to give you about 5 to 10 seconds to pause the video and then read the question and try it out. Try some of them out on your own first, and then go ahead and watch my what I do, because that way, as you watch me do it, you can kind of figure out where you went wrong in your thought processes, and that's probably one of the most important things to do for any test, really, whether it's chemistry or any other class that you have. Is to just know where in the thought process you're getting things wrong. So, all right, so just be wary of that, okay? All right, we're going to start with the first question, which has to do with bonding. So I'm going to give you a few seconds here to pause the video, look at the question, try these out on your own, and then we're going to go through it together. All right, so for bonding, remember that the principle that we use to understand what types of bonds will be made is the idea of electronegativity. And electronegativity charts can be given to you on the test if they are needed. Technically, sometimes they may just expect you to know the trend. Remember that the trend for a period for electronegativity goes right and up, okay, where up takes priority. And then based on the difference in electronegativity between two bonding atoms will determine the type of bond that it will make. So we have ionic, we have polar covalent and nonpolar covalent. And if the difference between these values is in one of these ranges, it will determine the type of bond it has. So if one element has a really high electronegative value and another one has a really low one, you might expect that this could be ionic, because the difference between their electronegativity values will likely be closer to 2. Now, as a general rule, ionic bonds are made between metals and nonmetals, right? So let me put metal plus nonmetal. And that's always because our metals have low electronegativity values, and our nonmetals typically have higher electronegativity values. So they end up just making these ionic bonds because of their electronegative values. So just be wary of that. Covalent bonds are typically between just two nonmetals plus two nonmetals. Okay, and the metallic bonds, which are the last ones we'd have to worry about, they're not entirely based off of electronegativity. They kind of do. There is an effect in their bonds in terms of electronegativity, but not too much. So metallic is really just two metals. So let me just put two metals here. And we don't really, for that one in particular, for this class, we don't look at the electronegativity values for that. We just say, oh, it's two metals, they're bonding, so we're just going to assume that's a metallic bond. So now, looking at the first question then, sulfur and phosphorus, right? So sulfur is right here, and phosphorus is right here. Now, that's two nonmetals, so I'm going to expect this to be a covalent bond. But what type of covalent bond will depend on the differences in electronegativity values. So we've got the difference of 2.58 and 2.19. Now, that, if you can tell, that's going to be slightly less than 0.4. So this is end up going to be nonpolar covalent, okay? It's going to be a little bit less. It's about 0.39. It's going to be a little bit less than the 0.4 value. So we're going to, for the sake of this class, that's considered a nonpolar covalent bond. Now we're looking at nitrogen and potassium, which is way over here, okay? Now you might notice this is a metal, or a nonmetal and a metal, okay? And that's, just knowing that, I'm probably going to assume that this is ionic, but we can check the electronegativity differences just in case. It's 3.4 minus 0.82. Yeah, that's going to be bigger than 2, so that's going to be an ionic bond. All right, we've got iron now. Iron is, we're looking at the transition, and we've got oxygen. Now, for some of these, you may find that actually, like in this case, the electronegativity difference does not fall, or is not greater than 2.0. Now, here's where people will get confused, because in general, when metals come together with nonmetals, they usually form ionic bonds. There's a rare case where they'll form other types of bonds. In fact, iron will form what we call sometimes a coordinate covalent bond, and that has to do with a totally different concept. Okay, in this case, we will still consider this ionic, even though it does not fall within our nice range of greater than 2.0 for ionic bonds. So don't be afraid of that. When you see a metal with a nonmetal, it's just assume that it's ionic, okay? The electronegativity differences can confirm our answers, but sometimes they're not going to be our determinants. Most times, we'll either use a combination of electronegativity and our intuition between two metals and nonmetals, or we can just look at, hey, this is just the metal and the nonmetal, and even though our electronegativity differences don't say so, nature, the way we find these two binding together, says that they come together ionically. So that's just what we're going to be doing. All right, now, carbon and hydrogen. Carbon and hydrogen, you'll notice those are really close to each other. The difference between those, the 2.55 minus 2.20, is going to be less than 0.4. So that's going to be a nonpolar covalent bond. All right, now oxygen and bromine. So oxygen's right here and bromine's right there. Yep, that's going to be greater than 0.4, but I don't expect that to get it's just slightly greater than 0.4, really. In some cases, some professors have used the cutoff as 0.5. So maybe in some classes, they may consider that to be a nonpolar bond. But for this question, because the difference is greater than 0.4 and we're using those cutoffs, we're going to assume that it's polar covalent. Lastly, we've got copper binding with another copper. So that's a metal with a metal. That's going to be a metallic bond, okay? Metallic bond. So that's kind of how you want to be thinking about these questions. Think firstly and foremost about what the identity is. Is this a nonmetal and a metal, or a nonmetal and a nonmetal, or two metals, right? Those will be principally what you want to use this or use as your determining factor of what kinds of bonds these will make. The electronegativity values can confirm those answers, but again, they may not even give you this chart on the test. They may just expect you to go off of trends or off of the thinking that we said of, oh, this is a metal with a nonmetal, so it must be ionic. Okay, so just be wary that even if they don't give you that chart, using your intuition can help you solve this question. Okay, now on to ionic naming. So I'm going to let you pause the video here for a little bit. Try this out on your own first, and then I'm going to go through this here in a second. All right, so with ionic naming, the one thing that you need to remember is that we always name the cation and then the anion second. So the cation first, anion second, and there are no prefixes that we have to add. Prefixes are specifically for covalent bonds because those ratios can change, right? I can have carbon monoxide or carbon dioxide or even carbon trioxide, but if I just said carbon oxide, I wouldn't be specific. Whereas in ionic naming, if I just say sodium bicarbonate, I know that it's going to come together in the same ratios. I don't have to designate sodium, tetrabicarbonate. It's just going to be in the same ratios every time, and so I don't need to put prefixes. So all you need, as long as you know the cation and the anion, the positively charged substance and the negatively charged substance, just put those in order of cation to anion, and you have the name. So number one, hopefully you were able to recognize that this is sodium. Okay, sodium, when it ionizes, right, we're talking about ionic naming, it ionizes into a 1+. I'm going to put Na+. Okay, and then it comes together with this substance. Now, this is one of the polyatomic ions that you had to memorize, and this is called bicarbonate. Okay, bicarbonate referring to this hydrogen that is now attached to what used to be carbonate. Carbonate is CO3 2-. We added an H+ to it. It became bicarbonate. So this is just straightforward. This is going to be called sodium bicarbonate. Another name for sodium bicarbonate colloquially is called baking soda. So that is sodium bicarbonate. All I had to do was name the cation first and then the anion second. You do have to have all those polyatomic anions memorized in order to answer these kinds of questions, okay? All right, number 2 says magnesium perchlorate. Okay, so I know magnesium, if I look on the periodic table, it's got a 2+ charge. Okay, cool. So when we're looking at the names and we're trying to figure out what these come in, what the ratios come into or what they look like, it's easiest if you just write the charges. Okay, so here's magnesium 2+. Now, hopefully you know what perchlorate is. Perchlorate is ClO4-. Okay. So when we're doing these, when these come together, they have to come together in a way that will neutralize the whole compound, meaning I need 2 negative charges to neutralize 2 positive charges, right? So that means I'm going to need 2 of these guys and 1 of these guys. So when they come together, all you have to do is switch the superscripts. You put the 2 down here and the 1 down here. That becomes MgClO4 and then 2, okay, on the outside, just like that. So it ends up looking, just like that. Okay, so just remember, put the charges and then flip the charges. Honestly, you don't even have to think about the concept of neutralization. If you just switch these superscripts, the 2 plus and the 1 minus, they always produce the right answer. So, all right, so now on to number 3. It says calcium bisulfate. Okay, calcium. I know it has a 2 plus charge, okay, and then bisulfate, that is not necessarily one that you have to have memorized, but you should recognize the pattern, right? You should know what sulfate is, and knowing what we've done with bi before, what bi means we've added a hydrogen to it. So this is going to be HSO4, and what was SO4 before? It was SO4 2 minus, okay? That's another thing you have to remember is all the charges on these guys, because it's going to affect how we change what the compound will look like, okay? So 2 minus, which means if we added H plus to it, bisulfate would have a 1 minus, okay? Which means, again, we're going to be coming together in a 2-to-1 ratio, and that ultimately produces this compound here, okay? That's calcium bisulfate. All right, aluminum chlorate. All right, aluminum is one of the few metals in the P block that we use a lot and that ionizes. So we got 3 plus here. Okay, and so that's aluminum because it's in the 3rd group or the 13th group, however you want to see it in the periodic table. And then chlorate is ClO3 minus, okay? ClO3 minus. So now just switch the superscripts, right? I'm just going to put Al and then parentheses ClO3, 3. Now, a lot of people maybe have asked, why do we put the parentheses? Well, the parentheses are to designate that there's 2 of this whole compound. It's not 2 of just oxygen or 2 of just the chlorine. It's 2 of the whole perchlorate molecule, or the 2 of the whole bisulfate molecule, or in this case 3 of the whole chlorate molecule, polyatomic ions I should say. Okay, so that's why we have to put those parentheses so that we designate which ones are pertain to which. Okay, all right, so now we're getting into compounds where we're dealing with a cation that can have a different type of charge. So remember, nickel is one of those transition metals. It's in the D block, which means it can take on a different type of cation charge every time. So with transition metals, we actually have to designate we have to put something extra in the name to designate which cation it is, right? We can have nickel 1 plus, nickel 2 plus. I think there may even be a nickel 3 plus, to be honest. And so we'd have to be able to designate which one's which. And we do that by way of Roman numerals, okay? Oops. Roman numerals. So if I say nickel 2 or nickel 2 sulfate or something, right? Nickel 2 sulfate would refer to nickel 2 plus, okay? So in this case, it's easiest first when you have a transition metal to look at the anion first. Hopefully you know that carbonate is a 2 minus charge, okay? Which means if they came together in a 1-to-1 ratio, let me get the 2 here. If they came together in a 1-to-1 ratio, that means it had to have matched that number, right? That the nickel charge had to have matched this in a perfect 1-to-1 ratio because they're in a 1-to-1 ratio. There's 1 nickel for every 1 carbonate ion. So that means the nickel must have a 2 plus, okay? So then what we would say is that this is nickel 2 carbonate. Nickel 2 carbonate because it's the 2 plus, which we knew by looking at the anion it had, and they came together in a 1-to-1 ratio, and then just added the anion's name, carbonate. Okay? All right, number 6, we've got copper. Okay, copper is another transition metal. So now that's key to saying, okay, now you need to look at this guy, okay? So this is called acetate. Hopefully that's another one that you have memorized. It looks like this, okay, as a 1 minus charge. And that's, the charges are going to be huge here. If you don't have the charges memorized, you're going to get these problems wrong. So it's really important that you have the charges memorized as well. Now, if you notice, they come together in a 2-to-1 ratio, which means that the copper must have had a 2 plus charge because they needed 2 of these in order to neutralize that copper. So then I would say, okay, this must be copper 2 acetate. Copper 2 acetate. All right. Now we've got this one. This one's doesn't have any transition metals, so I'm going to go back to aluminum. Aluminum is 3 plus, right? And then nitride. This is nitride. Okay, this is not nitrogen. Okay, nitrogen would just be a neutral neutral element with no charge. Okay, but this is nitride because we're talking about ionic naming. So nitride, when nitrogen ionizes, remember it has 5 valence electrons. Is it easier for it to gain 3 valence electrons or lose the 5? And it's easier for it to gain 3, right? And so it's going to take on a 3 minus charge. There's going to be N3 minus, which makes sense, right? They come together in a 1-to-1 ratio. So I'm going to call this aluminum nitride. Now, I don't need to say aluminum 3 nitride because it's not a transition metal. It's in the P block. It's going to always form a 3 plus charge, so I don't have to designate if there's another form of it. So this is just going to be aluminum nitride, just like that. just like that. All right, lead 4 sulfate. Okay, so now they've given us one that has its own Roman numeral. And so now what I have to assume is, okay, this is Pb, and this must be a 4 plus charge, okay? So that's easy. And then sulfate, if you, hopefully you remember, is SO4 2 minus. Oops, 2 minus, okay? So now just switch the superscripts. And then if they don't come together in the most reduced form, you reduce them down. So I'll show you what I mean. So I get Pb2 and then SO4 4, right? Well, technically these are even numbers. It can divide even further down, and so that's what we do. We're going to divide both of those by 4, and when we do that, we actually get this compound right here. So PbSO4 2. That would be your answer. Okay, now on to covalent naming. Covalent naming is slightly different than ionic naming in that we don't have cations and anions, but we do just name the first one and then the second one. So they're not necessarily in a particular order unless they're shown explicitly like this. And then what we do is we always assume that this guy will just call as by its name if there's just one of them, okay? So I'm just going to call this nitrogen, and then whatever comes after it is just going to be nitrogen something. Or here it's just going to be carbon something, or sulfur something. Until we get to a number greater than 1, then we add those prefixes, which are unique to covalent compounds. And so these are the prefixes. We have mono is 1, di 2, tri is 3. And then I have tetra and penta here with the parentheses of A, because there's sometimes, especially when we have an oxide, where we'll actually take off that A instead of adding it or instead of including it. And you'll see one of those examples here. Okay, and then so we're only going to add one of these prefixes to the first element if there is more than one of them. However, we always apply it to the second one. Okay, always. So all the second ones here should have a prefix next to them. So what ends up happening is we would call this nitrogen, okay, just regular nitrogen. And then since there's just one oxygen, we would call this monoxide, okay, monoxide. And so that'll end up being the name for this guy. So if we look at number 2, we've got carbon. Okay, I'm just going to leave it as carbon. And then we got 2 oxygens. So it's going to be dioxide. So the way that we name the second compound is we add this "ide" to the end. And that "ide" it's pretty intuitive. If it's oxygen, oxygen will just be oxide. Nitrogen would just be nitride. Sulfide. You'll kind of get a pattern for what these look like fluoride, chloride. And they'll always end in "ide," and that's just kind of characteristic of how we name these things. So number 3, we've got sulfur, and then we've got 4 oxygens. So this is where we actually call this tetroxide. Tetroxide meaning there's 4 of them, but we took off that A because it actually doesn't. It works out better linguistically if we just say tetroxide instead of tetraoxide. So we just put tetroxide. All right. Number 4, N2O5. So that's now we're changing the first one. The first element no longer has just one, so we can't ignore the prefix. We can't ignore not put a prefix on the very front. So, in that case, we're gonna call this dinitrogen. So there's 2 of them to designate that there's 2 of them, and then this is gonna be pentoxide, not pentaoxide, but pentoxide. So written like that. Okay. And then lastly, we've got sulfur, and then in this case, we got 6 fluorides. 6 belongs to the hexa prefix, so we're going to say the sulfur hexafluoride. And if you're looking for something entertaining to watch, you kind of like how helium raises our voices, this substance, sulfur hexafluoride, actually lowers our voices. It's kind of funny. But anyway, that's how we go about naming covalent compounds. Pretty straightforward, as long as you can understand that the very first element we don't put a prefix onto until there's more than one. The second one we always do, and then the second one we always add this "ide" to the end. Okay. All right, now on to Lewis structure. So here they want us to draw the Lewis structure for each compound and indicate any non-zero formal charge. Okay. And they want us to include the resonance structures and give the bond order. Okay, so what I'm gonna do is I'm gonna do the first 2 on one slide and the second 2 on a different slide. So on to nitrate. So nitrate, what we need to figure out is what the center atom is, and we can kind of assume it's nitrogen because it can make the most bonds, right? Oxygen can't, and plus a lot of times when they put one element in the front, it's usually going to be the center atom. So I'm going to put nitrogen here in the middle and then draw a skeleton. Whoops, let me fix that line there. Okay, and draw a skeleton. Give everybody an octet. And then figure out if it matches, if this structure matches the number of valence electrons from my compound. So I know that nitrogen is in the 5th group, so it wants 5 valence electrons. Plus, there are 3 oxygens times how many each of these wants? These want, and each of them wants 6, right? Plus 1 because we have a negative charge. So that's going to be a total of 24 valence electrons, okay? And if I look in the structure, I've got 1, 2, 3 times 8. That's going to be 24, plus this lone pair right there. So that's going to be 26. So I actually have too many. And remember, what we do in this case is we actually cancel out 2 lone pairs. Okay, so we get rid of the 2 of those lone pairs, and then make a bond out of it. Okay, and so not only is that you'll see that it minimizes formal charge, but it also matches us to the valence electron count. And now we can just double check to make sure that we have 24. Yep, and we have 24. If you were to count all these, here's 8, 8, and 8, so that's 24. Okay, so this is a potential Lewis structure, and it is charged. So I need to bracket this guy. Whoops, let me fix that other bracket. I do need to bracket this guy, and I know it has a -1 charge. But remember, we need to assign formal charges here. So now I know that formal charge is going to be want minus have, okay? And the want comes from periodic table, meaning what group are they in? If they're in the 7th group, or like fluorine, they'll want 7 valence electrons assigned to them, okay? This is not the same as an octet, right? This oxygen has an octet, but that doesn't mean it has a perfect formal charge, okay? Just because it has an octet doesn't mean it's going to match its formal charge. They're totally two totally different concepts, okay? So the want comes from the periodic table. For oxygen, it wants 6 because it's in the 6th group of the periodic table. So the way that we assign electrons, oxygen would eventually want 6 electrons assigned to it. But what does it actually have? It has, based on the Lewis structure, 2, 4, 6, 7. So it's 2, each of the lone pairs, we count every electron from lone pairs. So we know it has 3 lone pairs, so that's 6 electrons assigned to it. And then we only count half of a bond. Remember, a bond is made up of 2 electrons, and 1 electron will be assigned to the oxygen, and 1 will be assigned to the nitrogen. Okay, so in this case, oxygen has a total of 2, 4, 6, and then 7. Okay, so 6 minus 7, that's going to be -1. Okay, and we just put a minus in a circle like that. Okay, so it has a -1 formal charge. If I were to look at this oxygen, however, it's got 2, 4, and then half of each of these bonds, 5, 6, right? In this case, it's got a 0 formal charge because it wants 6 and has 6, okay? So in this case, I'm going to, let me go ahead and put this in. So in this case, this oxygen has a 0 formal charge. So technically, you don't have to write it, but I do put like a little, a minuscule 0 right there just to make sure, just to keep track of where I am. And then this oxygen is the same, so I'm going to put a minus charge there. Now, all that's left is this nitrogen. This nitrogen, let me put oxygen here, and the nitrogen here wants 5, right? It's in the 5th group on the periodic table. But if I look at the electrons assigned to it, it's got half of each of these bonds, and there's 1, 2, 3, 4 bonds. So that means it has 4 assigned to it in the Lewis structure, which means it has a +1 formal charge. So I'm going to put a plus right there. Now, if you were to add those formal charges together, you would get -1, which is what the charge is on the molecule. Now, a lot of people would be like, well, can't you make a bond between a negative and a positive so that you can minimize formal charge? Well, in this case, you can't, because nitrogen is in the 2nd group, on the 2nd period on the periodic table, which means it cannot expand its octet. It has a full octet, and it will not make a bigger bond than that. So what it's actually going to do is it's going to resonate this charge. So we have to actually draw the resonance structure. So here's a pre-drawn structure that I have ready. And then the Lewis structures, if you can see that this double bond could easily have been here or here. And so we have to account for that in the other resonance structures right here. So we draw our double-headed arrow, we get our new bracket, and then we just switch the bonds up, okay? And these are not actual structures. This is not actually how this thing looks in real life. Remember, resonance is different from delocalization. They're 2 different things. So this is not necessarily an accurate depiction of what these look like, but they do help us to keep track of these electrons so that we can figure out what the actual hybrid resonance structure looks like, which is a combination of all of these structures together to help us figure out what this would actually look like in real life. And that the hybrid structure is what we would consider delocalization. Now, they ultimately, they also wanted the bond order. And remember, the bond order for these things is going to be number of bonds, okay, over number of atoms that it's assigned to atoms. Okay, and that's just going to be atoms attached to the center atom. So in this case, we got 1, 2, 3, 4 bonds. Okay, that's going to be 4, divided by how many atoms have those bonds. So in this case, 1, 2, 3. So it's going to be 4 over 3. That's going to be 1 1/3 bond order. which is kind of like having a third of a bond, but it's in between a single and a double bond. All of these bonds have somewhere in between a single and a double bond, and it's around 1 1/3 strength of a bond. Okay, so that's really what that means. So that's kind of how we go about drawing not only Lewis structures and resonance structures, but figuring out the bond order, the formal charges, and making sure that we can ultimately get the right structures. Okay. Now, perchlorate, I'm going to assume that chlorine is the center atom because chlorine, even though it can't make the most bonds without expanding its octet, it can accommodate all the bonds by expanding its octet. So I'm going to assume chlorine's in the middle here. Okay, so I'm going to put chlorine here and then draw my skeleton. And then give everybody their octet, right? And then see if that matches my valence count. So I got 7 electrons from the chlorine, and then plus 4 times 6 from each oxygen plus 1, right? Because I've got that negative charge right there. So that's going to be 24 plus 8. That's 32. So in here, I've got 1, 2, 3, 4 times 8 is 32. So I actually have a potential Lewis structure here, right? I would technically just have to bracket this guy and give it a minus charge and say, okay, this is potentially one of those things, one of the Lewis structures. However, formal charge obviously plays a big role in this, and as we did in the last video, this oxygen is going to have the same formal charge because it wants 6. And how much does it have in this Lewis structure? Well, when we saw it like this with the 3 lone pairs, we know that it had 7 because it has 2, 4, 6, and then half of this bond, which is 7. So that means it's going to have a -1 formal charge. Whoops. It's going to have a -1 formal charge. So I'm going to give a -1 formal charge to all these oxygens here, okay? Now, what we need to figure out is whether the bond order is what the bond order is for chlorine. So chlorine wants 7, okay? But how much does it have in this structure? It has 4 because it has half of each of these bonds, right? So it's going to be a +3. +3, and so I'm going to put a +3 here. Now remember, when we have a negative next to a positive, it's more than likely going to make a bond out of that. So what will happen is this lone pair here will actually make a bond, a double bond with the chlorine so that it can minimize both formal charges. So that's what it's going to do. So I'm going to move that bond down. So that no longer has a -1 formal charge. So let me erase this lone pair and then make this bond. And now you can see that not only did this oxygen's formal charge go down to 0, but the formal charge on this chlorine went down to 2+ instead of 3+. And you can see that we could do that at least 2 more times with each of these oxygens, right? So I'm actually just going to make those. And you'll see that this actually makes 3 double bonds. And now we can see why there's this one where the negative overall formal charge comes from on this molecule, because there's at least 1 oxygen here that will have a -1 formal charge. And so like the answer before, I have the structure pre-written out here. Now let's go ahead and see what the bond order is. I have it written down here, but let's see why it's going to be 1.75. So we got 1, 2, 3, 4, 5, 6, 7 bonds. Okay, 7 divided by 1, 2, 3, 4 oxygen atoms. So that's going to be 7 over 4. And that's where we get the 1.75. Okay. And so each of these bonds will have each of the bonds between the chlorines and the oxygens will all have somewhere around a 1.75 bond order, meaning they will have somewhere between a single and a double bond, leaning more towards the double bond in this case, right? And these would be all the Lewis structures. You just have to rotate that negative formal charge around to make sure that it's on each of the oxygens. And then those would be all of your Lewis structures, okay? All right, let's do 2 more. We got Cl2O2. Now, I'm going to assume that that one of the Cl's is the center atom, because even though none of these atoms alone could accommodate for all the bonds that need to be made in this, right? Because I need there to be 1 center atom, and I need it to be attached to 3 different things. So I know the oxygen could technically do that, but it would take on a positive formal charge, and it typically does not do that, okay? So I'm going to assume first that chlorine can do it because it can make the most bonds by expanding its octet. So I'm going to put chlorine in the middle and then draw a Lewis structure, or a skeleton here, and see if it could possibly be one of my structures. So now everybody in this structure has an octet. Okay, and then I'm going to get 2 times 7 from each of the chlorines plus 2 times 6 from each of the oxygens. So in theory, it's going to be 14 plus 12, which is 26 valence electrons. And actually, that's exactly what I have here, right? Now, I just, so this does not have a charge on it. So I'm not going to draw brackets or put a charge on this because this will not have any resonance structures, okay? So, what I am going to do, though, is look at the formal charge. So I'm going to put formal charge here, and then want minus have, okay, want minus have. We'll do chlorine first, okay? It wants 7. If we look at this chlorine, it's got 2, 3, 4, 5. Okay, so I'm going to put minus 5 is going to be a +2 charge, +2. So you can kind of maybe tell that that's going to, we're going to try to minimize that somehow by making other bonds. All right, so now I'm going to look at I'm going to put +2 here. And then let's look at each of these oxygens. Remember, each oxygen wants 6. And in each of these here has a 7, right? Because it's got 2, 4, 6, and then half of that bond, which is 7. So that's going to be a -1. I'm going to put a minus here and a minus here. And then lastly, let's look at the back of this chlorine here. It wants 7, has 2, 4, 6, and then half of that bond, which is 7. So we're actually good on that one. So I'm going to put 0 here and then leave those there. Now you could tell that this negative charge these lone pairs could come down here and make that bond to minimize this formal charge, which is exactly what happens. So in this case, I'm going to erase one of those double bonds or one of the lone pairs here and make a double bond out of it here, just like that. And so that's ultimately what we get. Now, in terms of the bond order, the bond order would be different for each compound because there's no resonance. We're not going to be counting all the bonds over bonding over number of atoms in this case because we're not dealing with resonance structures, right? There are no resonance structures for this compound. So in that case, what we're going to do is just say, what is the bond order for this bond, for this bond, and for this bond? Well, you can tell that it's going to be 1 for the chlorine to chlorine bond here, and then 2 for each of the chlorine to oxygen bonds, simply because they have single and double bonds respectively. Okay, not too bad, right? All right, lastly, ozone. All right, ozone is very, confuses a lot of students, I think. So obviously there are 3 oxygens, and you can assume probably that oxygen is going to be the center atom, okay? Actually, let me draw this more over here. Okay, I'm going to put oxygen here, draw my skeleton, okay, and give everybody an octet. Okay, and then match it to this, to number of valence electrons I should expect. So it's going to be 3 times 6, which is 18 valence electrons. Here I have 1, 2 times 8 is 16, and then 18, 20. So I actually have 2 too many, right? And so in this case, we're going to do the same thing we did last time. We're going to cancel out one of the lone pairs here and one of the lone pairs there and make a bond out of it. And in that case, it would look like this, okay? So that would mean if we looked at the formal charges, right? Formal charge want minus have. Each oxygen wants 6, and this one has 7, which means it has a -1 charge. So it's weird because this has a 0. This compound is neutral, right? In theory, it should not have any charges spread out, but it does. And you'll see that it actually adds up to 0. But that doesn't necessarily mean that that there's not charge spread out. And this is one of the few molecules that actually does this. So, and you'll actually see that. So this oxygen here has 2, 4, 5, 6. So he's happy. He's actually got a 0 formal charge. So I'm going to put a little 0 there. But this oxygen's got 2, 3, 4, 5. Okay, so that's 5. Which means it's got a +1 formal charge. Now, you see a negative next to a positive. You're like, well, I can make a bond out of that, but oxygen can't do that, right? It cannot expand its octet. So, what that means is that this will actually have brackets around it because it will have resonance structures, okay? And actually, let me just show you what the actual things are. So, here it is, okay? And so you can see that it's going to spread out that charge as best it can simply because it's got... these formal charges. This oxygen could easily have the negative charge, or this one could. And so oddly enough, something that's not charged actually does have resonance structure sometimes when this charge is spread out. Now in this case, we would have to figure out a bond order like this, so we'd have 1, 2, 3 divided by 1, 2. So that's how we get the 1.5 bond order. Now that means each of these guys has a bond strength of 1.5 bonds. Okay. So I hope that you kind of felt a little bit more comfortable with this stuff. It can get a little tricky, but as long as if you can find a pattern, especially I've been trying to go through the patterns that we see and the patterns or the routine of drawing Lewis structures and such, that you can feel comfortable with this and be able to do this on your own, especially on the test. Okay, now we're going to kind of build off of this. Okay, now we're going to use the Lewis structures to predict something. So in this case, we're going to predict the electron geometry, the molecular shape, the angles, and polarity. So you can see how if you don't know how to draw a Lewis structure, you're going to get this other stuff wrong as well. So it's really important that you learn this stuff early so that later, because we'll probably be using Lewis structures later in the course as well for other things. It's really helpful to know how to draw a Lewis structure. So here they want you to determine these things. I'll give you a second to pause the video and try it out on your own. I have this chart here for you if you'd like to kind of go based off of that. Okay, so here, in order to determine these things, right, you have to draw the Lewis structure. So I'm going to put BR in the middle because I'm going to assume that BR can make the most bonds without expanding its octet. By expanding its octet, I mean. So in this case, I'm going to put fluorines all around this in the skeleton. Okay, just like this. And if you draw the Lewis structure correctly, that's how you know, or that's how you can get the rest of these answers correct. So if you did it correctly, you should get about 5 fluorines and a lone pair around the bromine. Okay, that lone pair is actually there. Okay, so that means that the steric number, okay, that steric number is going to be the most important thing in determining these things, okay? So the steric number here is going to be 6 because I've got 5 bonds, 1, 2, 3, 4, 5, and a lone pair, 1. So that's going to be a total of 6, which means bromine's got 6 areas of electrons around it, which means the electron geometry is the pair geometry is going to be octahedral, okay, octahedral. That's the term we give this when there's a steric number of 6. Okay, so I'm going to put Sn is equal to 6 just to help you out. So these are things that you should have memorized as well. Okay, so this hopefully you're able to remember octahedral, trigonal bipyramidal, trigonal planar, square pyramidal, square planar, tetrahedral. All those names, you should know what they look like, the steric number for them, the electron geometry, molecular shape, and the bond angles as well. Okay, all right. Now molecular shape. It would be the same as electron geometry if there were no lone pairs. Okay, if there were no lone pairs, I would say this is octahedra as well. However, obviously there is one lone pair here. So what that means is I'm going to have to figure out what this actually looks like in real life. And if you remember, when we have a steric number of 6, we have an axial plane. So here's my center atom, and it's bound to 2 things on an axial plane. And then we have like this square in the middle. So we've got X here, a bond here, and a bond here. Okay. In a square pair, when we get a lone pair on this, it actually starts at the axial end. Okay. So that means this actually looks like this. And when we look at the shape, we actually ignore this guy. So now it kind of looks like what we call a square pyramid. Okay, so we ultimately call this square pyramidal. However, it's interesting to note that this lone pair will actually push down these electrons, these bonds, a little further. So that will have an effect on our bond angle. So ultimately, we're going to call this square pyramidal, but it's not perfectly square because this is the lone pair here is pushing down on those bonds. So we're going to say those are less than, this would be 90 degrees. Okay, 90 degrees because each of these is 90 degrees from each other in a square, right? But they're slightly less than that because we've got that lone pair there, okay? Okay, lastly, we need to figure out whether this thing is polar or not, okay? And usually when we have an asymmetrical molecule, which is usually a case when we have a lone pair, it's going to be polar if the bonds are polar. And in this case, if you look at the electronegativity differences between bromine and fluorine, it's quite large, right? Bromine is 2 periods below fluorine, and that gives fluorine a lot more electronegative strength. And so there is a dipole in them. And if we were to draw that structure again, right, you can see why if there's a lone pair down here, there's an overall dipole upwards, even though all of these ones in the middle cancel each other out, right? Because this one is not being canceled. This dipole is not being canceled out by anybody. So this thing ultimately is polar, which will generally happen for molecules that have a lone pair. And there are a few cases where lone pairs actually make the molecule symmetrical, and so it actually cancels out all the vectors. But for the most part, when lone pairs are present, it's going to make it a polar molecule. Okay. All right, now SOCl2. put S in the middle here. I'm going to draw my skeleton. We did a lot of Lewis structures in the last problem, so I'm just going to show you what the Lewis structure should look like. You should have sulfur in the middle with a lone pair, and then double bound to oxygen, and then single bound to the two chlorines. That's ultimately what it looks like. Now, the steric number here, the steric number is lone pairs or pairs of electrons around this, whether they're lone pairs or bonds. And so in this case, we got a steric number of 1, 2, 3, 4. So this is going to have a steric number 4, which means my electron geometry, without even looking at lone pairs, should be tetrahedral. Okay, that's just by definition. So tetrahedral. Now, if my molecular shape would be tetrahedral if there were no lone pairs. However, I do have a lone pair, and when we have one lone pair on a steric number of 4, it actually becomes trigonal pyramidal. Okay, trigonal pyramidal. Now, trigonal pyramidal makes sense because in theory we have two bonds that are this way. So I'll put the chlorine down here and the oxygen down here, and then we have two bonds that are going in and out of the page. So we got a chlorine down here. Actually, let me put the lone pair up here. And then we've got the sulfur coming out this way. Or the oxygen coming out this way, and with the sulfur here in the middle. And you can kind of tell that this is, triangular here, the base, and that there's overall, here are dipoles. There are actual dipoles here, which we'll go over here in the polarity in a second. But that makes this thing a little trigonal pyramid, right? It's a pyramid with like 3 bases. So the bonds here, in theory, would correspond to the tetrahedral formation, which would be 109.5. But in this case, because we have that lone pair pushing things down further, it actually ends up becoming just less than 109.5. Okay, less than 109.5. All right, so polarity, we were talking about these dipoles being here. Yeah, there is going to be a dipole between sulfur and chlorine. Chlorine is more electronegative than sulfur, but also oxygen is way more electronegative than sulfur. And so there is going to be a dipole on each of those, which make there a dipole overall going downward on this molecule. So this thing is polar. Okay, yeah, and then just remember that this thing is less than 109.5. Okay. All right, lastly, we've got this boron trifluoride. Okay, so I'm going to put boron here in the middle and then draw my Lewis structure. Ultimately, there's just going to be these 3 bonds and no lone pairs on this boron. And you'll know the reason why is because this boron will actually be happy without an octet, even though because it's got a minimized formal charge. It's got a 0 formal charge as it does that. So boron is one of the few that actually does this. It's just kind of an anomaly in the rule. Now, if I look at the steric number is going to be 3, right? I've got 3 bonds and no lone pairs. So that means that I'm going to be following the trigonal planar electron geometry, okay? Trigonal planar electron geometry. And if the molecular shape would be the same if there are no lone pairs, and there are no lone pairs here, so it actually is going to be the same, okay? Which would mean the angles here are going to be exactly 120 degrees, and that makes everything symmetrical, so this is going to be nonpolar, okay? Nonpolar. Because even if they are polar, which they are actually, these bonds are polar, they pull equally each direction. I haven't drawn this in the right way, I guess. I have to draw this in more of a triangle so that you can see why these vectors all cancel each other. So I'm going to put this here. Technically, these vectors here add up to an overall vector here, which actually cancels out the vector up here. And then so on and so forth. You can kind of see how it goes around the molecule. So overall, because it's symmetrical, which is typical of when our molecular shape is equal to our electron geometry, we will have a nonpolar molecule, even if the bonds are polar. All right, in the next problem, we're actually going to be applying an old concept to a new concept. So we're going to apply dimensional analysis to now looking at how many electrons are in a particular molecule given what the Lewis structure looks like. So we're going to be combining Lewis structures with dimensional analysis. So this is a pretty common question on the test. I would almost assume that any test that they give you at this point in the semester is going to have a question like this. So whenever I see a number like this really quick though, and I see it in milligrams, I automatically in my head, I already turn it into grams. So I don't have to put it into the dimensional analysis. It's almost like I just don't want to have to put too many extra numbers that I don't need, okay? So in my mind, this is actually 0.1053 grams, okay? And that's how I'm going to read it. So now it says, determine how many bonding electrons are in 0.1053 grams of bromine trifluoride is what this would be called, right? So in order to do this correctly, you have to draw the correct Lewis structure. And if you do that, we've done that in a previous problem and previous videos, but you should get this. So it's going to be 3 bonds, each one bromine bound to 3 different fluorines, right? And then you'll actually end up finding that there are 2 lone pairs on that central bromine. So that's where we need to start. Now, in the dimensional analysis, you always start with the measured value, which in this case is this number here. Okay, so I'm going to start out my dimensional analysis there. Okay, so there's my number. I know I have that many grams of bromine trifluoride. Now, the next thing is to know what am I converting to? And in this case, we're going to use the molar mass of bromine trifluoride because I need to be able to turn this, I need to be able to use the mole in this case so that I can turn it into molecules and then determine per molecule of bromine trifluoride how many bonding electrons there are, okay? So I'm going to do that, and you have to use the molar mass, the molar mass of that. Which happens to be 136.9 grams per 1 mole. So now if I were to stop here in my dimensional analysis, I would find how many moles of BRF3 I have. But that's not what they're asking. What I need to figure out is how many molecules of these I have, and then ultimately how many bonding electrons per molecule I have. So I'm going to use Avogadro's number, and so that's just going to be 6.022 times 10 to the 23. If I were to stop here, it would tell me how many molecules of BRF3 I have. It would tell me how many of those, this whole thing that I have, okay? But ultimately, what I need to find is the bonding electrons. So I know that per 1 molecule of BRF5, one BRF3 molecule has how many bonding electrons? It's got 2, 4, 6 bonding electrons. 6, I'll just put BE. Okay, so that's going to be my conversion factor for this. So I'm going to put a BRF3 molecule has 6 bonding electrons. And then once you found that the unit that you're looking for is on the end on the top, that's when you stop, okay? And then just make sure that all of these are canceling, okay? That's how I'm moving from each one to the others. I'm finding, okay, what goes from grams to another unit that I need? Okay, I needed moles, so I'm going to find the molar mass. Then I needed to go from moles to Avogadro's number of molecules. I need to go from moles to molecules, and I knew I could use Avogadro's number to do that. And then to get from molecules to bonding electrons, I had to find out this conversion factor and then apply that to my question. So ultimately, if you do that right, including sig figs, right, this is 4 sig figs right here, and it's usually, our sig figs are usually based off of the measured value that they give us, this very first number. So our answer should have 4 sig figs, and if you do that correctly, you should get about 2.779 times 10 to the 21 bonding electrons. Okay, so that's our answer right there. All right. Another type of question that they'll ask you is about sigma and pi bonds. Remember, sigma bonds are made up of overlapping hybridized orbitals. I'll just put overlapping hybrids. Okay, meaning that's going to be like an sp with another sp2 maybe, or so on and so forth. Hybridized orbitals will be overlapping, whereas pi bonds are unhybridized overlapping unhybridized p orbitals. So I'm going to put overlapping, I'm just going to put overlapping p's. Okay, and that's where you'll typically see a double bond or a triple bond. And in fact, in a structure like this where there are some implicit bonds, there are actually, all the pi bonds will always be explicit. So here's one pi bond, here's another one, and here's another one. So I'm going to actually put the 3 right there. That's pretty easy. The harder part is figuring out sigma bonds, because in this type of structure, there are a lot of implicit bonds, okay? So remember that in a structure like this, at each bend, there's a carbon, okay? There's a carbon there, a carbon there, a carbon there. And so at every one of these, I'm just going to put a carbon, okay? Even at the end of that line right there. And that anywhere that's possible, there's going to be a hydrogen on those carbons. They explicitly show this hydrogen bound to this carbon only because they had to explicitly show the stereochemistry, okay? So, with the chiral center, that's what I'm referring to. So, in this case, I'm going to draw all the implicit hydrogens. So there's a hydrogen here, a hydrogen there, a hydrogen here. And then not here, this already has the 4 bonds that carbon makes full. So it's not going to have any extra hydrogens there. But there should be an extra one here, right? So it's got 1, 2, 3. And then this is its 4th bond. So that's how I'm figuring these out, as I'm counting. Okay, each carbon can make 4 total bonds. How many of them are in a double/single bond, and whatever's left will be a hydrogen. So in this case, I'm going to move up here. I'm going to say there are 2 hydrogens on here because it's already making 2 different bonds. 2 hydrogens on this guy. 2 hydrogens on this guy, and then 3 hydrogens on this last guy here, okay? And those are all sigma bonds, okay? So if you had not taken into account all these implicit hydrogen bonds, or bonds with hydrogen and carbon, you would have actually gotten this question wrong, okay? So it's important that you know how to read this structure. So now we just got to count how many bonds there are. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. Okay, so a total of 27 sigma bonds. And you're welcome to try that out on your own as well. I recognize I didn't give you a time at the beginning of the video to pause, so I apologize for that. I'll do that on the next one. But that's kind of how you should know how to find the sigma in the pi bonds. All right, on a related concept, we're actually going to be covering isomers. So there are different kinds of isomers, and in this case, when they're asking for all possible isomers of pentane, that could be constitutional, right, where we have different bonds being made, isomers, or they could be geometric isomers like cis and trans. Typically, they're not going to ask you for diastereomers or enantiomers when they're asking for this kind of question. So it's mostly just going to be constitutional and geometric. Okay, geometric meaning cis and trans. So they're asking draw all possible isomers for pentene. Okay, C5H10. Well, let's just draw the first structure really quick. Okay. C5 means there's 5 hydrogens, right? So there's 1, 2, 3, 4, 5 carbons. Sorry, I meant carbons. 5 carbons, so it's a 5-carbon chain. But there should be 10 hydrogens. And if I count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I have 2 extra hydrogens. Now, hopefully you remember from previous videos when we're short 2 hydrogens, that actually means that we have a degree of unsaturation. That could either be manifest in a cyclization, meaning it's become a circle, right? It's bound in a cycle, or it could mean a double bond. So in this case, I'm going to just assume a double bond, and this is going to be my first structure of one of the possible structures for pentene. So I'm going to move down to here and show you the very first structure. So this is also another one, right? I didn't actually write this one, but that's another one, right? I could easily put the double bond on the end there, or I could put it where I had it before. But notice that this is going to probably have a cis or trans isomer, because if I look down this bond, okay, remember, cut it perpendicularly, label side 1 and side 2, and then circle the biggest group on each side. Here I've got this big group, and then here I've got this big group. And so when I look across the bond, this is going to be the trans version. So what that means is I can flip this side over to make the cis version, which would be this, right? So those are at least 3 structures that I can draw for pentene so far. I could also do this structure. All I did here was, now that I've saturated, or I've used as many isomers of the parent chain of 5, meaning they're all in one line, right? Parent chain of 5. I can change the parent chain number and then just move around one of the groups. So in this case, what I did is I changed it to a 1, 2, 3, 4 carbon chain, and then just added this guy here instead of continuing it off that guy. Does that make sense? So we've changed the parent chain, and now we're just trying to figure out other ways to draw this. So I could also do this structure where I just, instead of putting the bond here, I actually put it right here. Okay, and that would actually end up being a different structure. Well, we actually also move the double bond over there, right? And so we get this structure here. I can also put have this same structure, but then put the double bond on the end here. And then lastly, you can actually have a cyclization. Okay, a cyclization is also a degree of unsaturation, and we still have C5, 1, 2, 3, 4, 5, and then each of these has 2 hydrogens, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so those are kind of how you draw the isomers for these guys. Just figure out your very first structure. Okay, the very first structure is just going to be the first step. As long as you can do that and kind of follow these patterns, you'll be okay on drawing isomers. When you have a double bond, that's when you can have cis and trans. Sometimes you may not have a cis or trans option. Like if it had been this molecule here, there's actually not a cis. Technically there is a cis or trans for this one, but like this one right here, this one has 2 hydrogens on the end here, so there's not one group that's bigger than the other. Okay, so sometimes just recognize that sometimes even though there's a double bond, that structure may not in and of itself have a cis or trans isomer version. And then what we did is we just changed the parent chain count, right? Here's my parent chain. I had a parent chain of 5, okay? Parent chain is just the longest chain of carbons in one compound. Here, this is 5. Once I ran out of the 5, I changed it to 4, and then just added, just threw another methyl group somewhere else. So here's the 4 again, added it here, and then just kept it here, but then just moved that double bond over. So hopefully that makes sense. I wanted to make sure I really got that down. If you have more questions, I do have previous videos that explain how we get these types of isomers. Okay, more on isomers as well. We're now kind of a review of what we were doing a little bit before. The cis or trans isomer is can kind of get confusing. So what you do, remember, cut it perpendicularly first. label side 1 and side 2. Circle the biggest group on each side. So in comparison of carbon, the CH3 group here on the end, that's going to be bigger. So I'm going to circle that group. But then if I look at carbon over here, CH3, okay, we determine the biggest group by molecular weight, okay? So what I'm doing is I'm actually comparing carbon's weight to oxygen's weight, and whichever one is heavier is going to be my bigger group. So when I look on the periodic table, whichever one weighs the most is going to be my bigger group. You'll actually find that oxygen is heavier than carbon. So that would make that the biggest group. So if I looked across this bond parallel now instead of perpendicular, you'll notice that they're on the same side. So this is going to be the cis form of that compound, okay? That's what they're talking about. So again, let's do this on number 2. So number 2 says has this compound. I'm going to cut it perpendicular down the middle. I'm going to circle the biggest group on each side. On each side, okay? So that means I'm going to compare, let's go one side 1 and side 2. So I'm going to compare bromine to carbon and carbon, okay? Now, bromine is definitely heavier than carbon, right? So I'm actually going to just circle bromine because it weighs the most. And same with chlorine, right? Chlorine in comparison to carbon weighs more. So when I look across this bond like this, I notice that they're on opposite sides. And opposite is refers to the trans version, okay? So here's my cis over here, and there's my trans. All right, now number 3, this is going to be a little tricky because you may be tempted to say, well, this could be a cis or a trans molecule, but it actually can't have either. If you remember in the last one, we had a double bond that had 2 hydrogens on the end, so it actually didn't have a cis or trans version. But and the same is similar in this case. Technically, we have the biggest group on this side, but if I look at side 2, these guys are the same exact group. So in this case, this does not have any cis or trans. Okay, there's none. It's not going to have. It's going to be the same no matter what way you put it. Okay. So number 4, we have 2 double bonds. We have got one right here. Now you can kind of tell this is not going to have a cis or trans version because there are 2 hydrogens, which is the same group. So there's not going to be a cis or trans version of that guy. So I'm going to ignore that guy. But I know I'm going to have a cis or, I can see if I can have a cis or trans version on this guy. Well, comparison to hydrogen, this group is going to be bigger, right? This is carbon CH3 group on the end here. And then on, let's say, level side 1 and side 2 here really quick. And then on this side, obviously, this group is going to be way bigger than just this single hydrogen here. So that means when I look across the bond, parallel to the bond, they're on opposite sides. This is actually going to be the trans form of this compound. So just remember, cut it perpendicular, label side 1, side 2, and then circle the biggest group according to atomic weight. Okay, according to atomic weight. It shouldn't be more complicated than what I've shown here. You'll get way more into this in organic chemistry, so I wouldn't really worry too much about the details on like what if this is slightly bigger than this. It's going to be pretty obvious on the test. Okay. So overall, we've talked about a lot of different isomers, right? We talked about constitutional isomers, which is what we just covered. We're talking about geometric isomers here. And we've also in the past talked about diastereomers and enantiomers, which are type of what we call stereoisomers, meaning they're different in 3D space. Okay, everything's bound the same, but as far as 3D space goes, they're different. And that's entirely centered upon this idea of chirality. Okay, chirality, I looked this up, and hopefully this definition will help you, is the aspect of a structure or property, such as the configuration of a molecule or the spin of a particle that renders the structure or property distinguishable from its mirror image or symmetrical opposite. Meaning, if you, for example, we talked about facing your hands towards each other, right? They're mirror images of each other in theory. But once you try to superimpose one on the other, they're different, right? They actually look different, and your thumbs end up on the opposite side. Okay, so our body actually exhibits chirality, but as far as molecules go, for molecules to be chiral, there has to be an atom that's bound to 4 different groups. Okay, 4 different. I'll just put different up here, different groups. And I'll show you what that means as we look at these compounds. So here they're asking us to identify all the chiral centers in the following compounds, meaning there's going to be a carbon or some molecule in which we might expect there to be a non-superimposable mirror image based on the fact that the atom or the center atom is bound to 4 different groups. So anytime you see a chain like this carbon here is bound to at least 3 hydrogens, right? So it is not chiral, right? This carbon is bound to 2 hydrogens. So I'm actually going to ignore all of these carbons right here because none of them are bound to 4 different groups. So I'm going to ignore all of those, and in this chain as well. So I'm going to ignore all of these. So if I look at this carbon here, it's actually bound to 2 hydrogens, so I cannot count that. And same with this guy, right? It's in the same case. Now, if I look at this carbon, Okay, let me erase things so you can kind of see this. This carbon is bound to a hydrogen. It's bound to this group. Okay, it's bound to this group, which does differ from this group, right? It's got a double bond. It's not exactly the same. If it was exactly the same as this top group, then it would be the same compound, which would make this carbon not chiral. And it is bound to this group, and those are 4 different groups right there. Okay, so this carbon, I'm actually just going to highlight it with let's say an orange right here. That carbon is chiral. Okay, that carbon is chiral. Because we got those 4 different groups, and you may have been confused as what groups meant. Hopefully, you can see that it's that whole chain that follows it. Okay, we're not just looking at this group here and this group here. If you had done that right, you'd say, oh, maybe these are the same group, so that's not chiral. But we have to look at the whole chain behind it. Okay, so that's what makes it a chiral center. And in theory, we could look at everything else. We can, but I'll just let you know there's not any other chiral centers. You could look at this phosphorus and say maybe that's chiral, but we don't know what this is. Okay, if it was specifying what that was, there's a possibility that this could be a chiral center because this is one group, right? That's another group. This is another group, and that could, in theory, be another group. But if this is maybe the same as these, then it's not. We can't tell. So because it's not specific, we're not going to be confident in saying that that's a chiral center. So I'm just going to leave it just there. We only have that one chiral center there on that carbon. All right, now if we look here. Typically, when I look for chiral centers, I'm looking really just at carbons because really anything else typically does not have a chiral center unless it's like randomly phosphorus that will make 4 bonds or expand its octet to make those 4 bonds and minimize its formal charge. But for right now, I'm just going to look at carbon. So if I look at this carbon, right, it's got 1, 2, and 3 bonds, and so I'm not at 4 yet, so I'm not going to count that as a chiral center. This carbon right here is bound to 2 different hydrogens, so those are one of the same group. And here as well, right? I'm actually just going to draw out all of these or exonate all of these so that you can see that none of those are going to be chiral. And we could even just look at this phosphorus really quick, right? This phosphorus is bound to this group, it's bound to this group, and it's bound to this oxygen, but it's also bound to another oxygen. You may think like, oh, this is double bound and this is single bound, but remember, these resonate, right? And so this will actually come down here, bump this lone pair up there, and it'll resonate, and those are actually the same compound, so that's not going to be chiral, okay? It's not going to be chiral. So lastly, I purposely left this one for last, right? This carbon is bound to this OH group, this group here, and what's implicit here that's not written? Another hydrogen, right? That's 4 different groups. So because that's 4 different groups, I'm going to go ahead and dot that. That's going to be a chiral carbon. Okay, and it ends up being my only chiral carbon in this case. Nitrogen, right? You technically look at this, but it's bound to 3 different hydrogens, three of the same hydrogens, right? So it's not going to be a chiral at all. Now, whenever you see a ring structure like this, you can assume that none of those carbons are going to be chiral because they're all double bound like this. Now, what I mean by ring is that they're all rings with double bonds, which we call benzenes. But technically, I guess in theory, if there's a ring like this, right, you can have a carbon. So don't get confused by when I meant ring when I meant benzene. Okay, so none of these carbons are going to be chiral. This carbon is bound to 2 hydrogens, so I'm going to count that as a no, and this one is as well. And so there are actually no chiral centers in this compound here. So I'm just going to leave that blank. All right, lastly, this is testosterone. Okay, this is actually what testosterone looks like. And we're going to look at how many chiral centers this thing can have. So this one is bound, this carbon right here is bound to 3 different groups, so I'm going to cancel that one. So is this one, so is that one. Okay, but if I look here, this is 2 hydrogens, so I'm actually going to cancel those as well, and this one as well. And all of the ones that are just kind of like out on their own like that, okay? Just because they're not, I just know by default that they're not going to, because they're bound to 2 hydrogens, that they're not going to be chiral centers. So I'm going to go ahead and erase those, but hopefully you remember that that's where we're canceling out those chiral centers. Now, if I look here, okay, it's kind of confusing because we're in ring structure, but hopefully you can follow along that this structure, okay, it is not the same going around this way, okay? If this, let's say I have 2 rings like this, okay, this carbon would not be chiral until I made this group different, okay? Now this would be chiral because now I have this group and this group which don't look the same, right? Because this guy's got this little lump over here. So in this case, you can kind of see that this group right here is not the same going around on this side. Okay, and then we've got this carbon over here and this carbon up here. That's 4 different groups. Okay, and so I'm gonna go ahead and dot that. that's going to be one of my chiral centers, okay? Now, I'm going to look at this carbon right here. I've got this group right here. I've got this group right here. It's kind of hard to, you may get confused as why, what groups are what. But remember in the example I just gave you, if it doesn't look the same going one way as it does the other, meaning, I had this here, okay? This looked identical going this way as it did this way. It's the same, right? But the second I put this here, this is now different than it was going this way. And so now that becomes chiral simply because this side doesn't look the same going around the other way. So anytime that you can see that, so in this case, going down, if I'm going down this way, it's not going to look the same going down this way. And so that's why I can assume that it's not, that those are different groups. And ultimately, that's going to be a chiral center because those are 4 different groups. And pretty much any of the carbons that you see in these ring structures, in these hormones, the steroids that we go over in organic chemistry, all of these will be chiral centers, okay? And you can kind of check for yourself too that they're just not going to go they're not going to look identical going one way as they do the other on the ring structures. And so those are actually all the chiral centers on that substance. So you can have multiple chiral centers and thus very many diastereomers, right? There's different types of stereoisomers that you can have with that compound. Okay, now in the next problem, we're actually going to be covering bonding theory. So when I say VB, that's Valence Bond Theory, okay? And then MO is Molecular Orbital Theory. Remember, those are the 2 theories that the bonding theories that we've been covering in this unit, okay? So Valence Bond Theory, which has to do with like the hybridization, right? Hybridization, like having sp2 overlapping with the atomic orbital sp or whatever. Whereas molecular orbitals, we had those like funky diagrams where we had to fill in the electrons, right? We had 2 s orbitals come together and create a bonding orbital and an anti-bonding orbital and such. Okay, that's molecular orbital theory. So just to kind of remind you what that looks like, what each of those are. Now, with that in mind, what we're going to do is determine which of these is better at what, okay? And it's really important because you actually find out that one of these theories is superior to the other, meaning it's actually way more accurate and way more useful than the other. Okay, so calculating bond energies. When we're hybridizing orbitals, when we're talking about overlapping hybridized orbitals, we have never talked about the energies, bond energies. We've never talked about what the bond energy of, let's say, an sp overlapping with an sp2 energy is, because there isn't one. We can't calculate it. This is just a shape theory. It's like determining what this would look like if they're determining by looking at hybridization and VSEPR, right? So it's actually not great at calculating bond energies. However, molecular orbital theory is, right? When we were drawing those diagrams, these are energy diagrams, right? When the reason we draw one below and one on the top is because that's designating energy. The antibonding orbital, the sigma star, right, is in higher energy than the sigma, and that's why we draw it like this, is because these become an energy diagram. And so we actually are able to calculate these. It does take a lot of it does cost a lot, meaning we have to use a supercomputer for a lot of molecular orbital theory stuff, but it's good at doing it. So only MO can do this. Calculating bond order. Now with VB, with valence bond theory, when we're looking at hybridization of orbitals, right, we were able to draw those structures where we had sp overlapping with another sp maybe, and then there were 2 unhybridized p orbitals on each of these. So when we were drawing these, we were like, okay, yeah, here's my sigma bond and here's my 2 pi, right? Here's my 2 pi. And so that would be a triple bond. So we were able to estimate, we were able to kind of guesstimate what the bond order would be, being like, okay, if this is a single bond, then this must be a bond order of 1. If this is a double bond, then it must be a bond order of 2, and so on and so forth. But it's mostly just an estimate, and we'll see how that differs from MO theory later. But MO theory is actually able to do it very well as well, right? When we take bonding minus anti-bonding over 2, like electrons in bonding orbitals minus electrons in anti-bonding orbitals divided by 2, and that gave us our bond order, right? And in those kinds of situations, we can actually get like 1.5 bond orders, right? Or 2.5. And so that's how it differs from VB, is in that VB can only estimate these things, whereas MO can actually accurately depict what the actual bond order will be. Okay, so understanding magnetic properties. Now, we never talked about magnetism when we're referring to valence bond theory, right? We never really talked about magnetism because it doesn't do anything about it. It doesn't tell us anything about magnetism. But molecular orbital theory does. If you remember, when we were making these diagrams, we would determine whether they were paired or unpaired, right? And if they were paired, then they were diamagnetic and thus not magnetic. Or if there was an unpaired electron somewhere, then we would call it paramagnetic, which would make it magnetic or give it magnetic properties. And so only MO can do that, okay? So as you can see, MO is the more superior theory because it can do a lot more stuff than valence bond theory does. Now, predicting molecular geometry. This is where I have a lot of conflict with other sometimes TAs and stuff, because technically VB does not tell you anything about that, okay? Valence bond theory by itself cannot tell you anything about the molecular geometry. In order for valence bond theory to tell you anything about molecular geometry, you have to include VSEPR, okay? So in my opinion, okay, this is strictly my opinion. My opinion is that it's only MO that can tell you molecular geometry, because we can actually predict it with a supercomputer, use a supercomputer to actually and incorporate all the data and get a structure out that will actually be super accurate if we use MO theory. However, some professors may say that valence bond theory can do this, but they can only assume that if they're equating VSEPR with valence bond theory. Remember, VSEPR is valence shell electron pair repulsion, where we were talking about octahedral or trigonal bipyramidal. Okay, those shapes. That's the theory that we were using to get molecular geometry. But later, but they're assuming, what they assume is that that's part of valence bond theory, and I don't know why they assume that, because technically it's not. But valence bond theory, I guess, what they talk about valence bond theory in terms of VSEPR is they say that valence bond theory explains VSEPR by using hybridization and such. But in my mind, and when I was tested on this concept, I was tested on these separately, meaning that this was the answer on my test, okay? But what I'm saying is that may not actually be the answer on your test, because I've seen professors change this and say, actually, VB can do this as well, because technically it has VSEPR under its belt. So in my opinion, what you'll have to do is actually ask your TA or your professor what they would prefer, or what they have specified in class about this, to know what kind of how they'll ask this question. Okay, so again, the first three I'm pretty confident will be the same for your professor and your class. This last one, though, I would ask either your professor or your TA about. Okay. All right, so now on valence bond theory, now we're going to apply this to drawing the actual structures. Now, I've heard that some classes are turning into multiple choice only tests, but if you still have the free response version, you're actually going to have to draw these, and so it's really important that you know how to draw these. So the first thing that you should be able to do in drawing these structures is draw the correct Lewis structure. Okay, we're going back to that. If you don't know how to draw the correct Lewis structure, you will get these problems wrong. So it's really important that you know how to do that. So first, what we're going to do is do hydrogen cyanide is what that's called, ethene, and then carbon dioxide. Okay, you can go ahead and pause the video and try this out on your own really quick, but I'll be going over those here right now. Okay, all right, so first, draw the correct Lewis structure. So I'm going to put carbon in the middle and then hydrogen. Now, you should get a triple bond between carbon and nitrogen here with a lone pair on that nitrogen. And this would have a zero formal charge over everybody. Okay, so this is ultimately our Lewis structure. Now, what you have to figure out is the hybridization based on the steric number of each substance. So in this case, hydrogen will never hybridize. It's actually always going to just keep its s orbital. So I'm going to draw its s orbital here and then just put the hydrogen above it just to know what I'm talking about, okay? Now, carbon has a steric number of 1, 2, okay? So steric number, remember that number. Remember that concept. It's where we're counting number of pairs or number of bonds and number of lone pairs. And in this case, we have only 2 bonds, and so the steric number is 2. If my steric number is 2, okay, that means I need 2 orbitals to hybridize, okay, which means I'm going to be hybridizing an s and a p to get 2 sp orbitals, and then left with 2 unhybridized p orbitals. Now we do that. Remember why we do that? We do that because carbon needs to be able to spread out its electrons into each orbital so that it can use those orbitals to make bonds. So now I've got 2 orbitals, which means, remember, when the steric number is 2, what shape was that? That was linear, right? So I'm actually going to draw these in a line with each other. So here's one sp orbital. Now, really quick, why do I draw it like this? Because when we mix an s orbital, here's my s orbital with another p orbital, remember that one of the lobes of the p orbital is out of phase with the other, just like if I were to draw a wave like this. this part of the wave is out of phase with that part of the wave, right? This is a different phase. It's in the negative phase, and this is in the positive phase. And all waves do this. And so remember, orbitals are just the wave form of this guy. So just remember that. And that when they mix together, this obviously is going to add to that guy. So we end up getting this funky looking structure where the top lobe overrides or is like almost twice as big as the second lobe. So that's why I'm drawing it like this. And then what I'm going to do is I'm going to draw it. Remember, I'm drawing it linearly. So here's my other sp orbital. Now, if you remember, we left 2 unhybridized p orbitals on this carbon. So I'm going to draw one of them here. And remember that the p orbitals, there's a px, a py, and a pz. I'm going to assume that I use the px to make this sp orbital here, just to make it simpler. So I've got a py up here. And then I'm going to draw, hopefully you can kind of see this in 3D, but I'm drawing a lobe coming towards you, coming out of the page, okay? And then the second lobe in the back, okay? So here's one of the lobes down here for the py, and then this guy in the back is the pz, okay? Pz. So hopefully you can kind of see that in 3D, but now I'm going to draw the other nitrogen. I'm going to draw the bond here for nitrogen. And actually, let's just go ahead and look at the structure. It might just be easier if I just show you. Now, what I'm doing is drawing the nitrogen side. So I know the steric number is 2 because I've got a bond here and a bond here, or a lone pair there. Okay, so now I've drawn my S over here. Here's my hydrogen. In the middle here is where my carbon would be, and here is where my nitrogen would be. And remember, if the steric number is 2, I've got 2 unhybridized p orbitals, and here I've drawn them. Okay, here I've drawn them. And then there's some coming out of the page and going into the page like that. And so they're binding in the back and in the front, and then on the top and on the bottom. Okay, can you kind of see that? And then here's my this would be my sigma bond in here, and then here's one pi bond, and then on the sides and the back here, here's another pi bond, right? So this is what this ultimately looks like. And we were able to use the steric number for multiple things, right? We were able to use it for the hybridization. And we're able to figure out what this looks like shape-wise, right? We used steric number a lot when we were looking at a VSEPR. And so I combined both of those to make sure that I was this was combining VB, Valence Bond Theory, with VSEPR to overall get this structure. So this is ultimately what you should get. Hopefully that kind of made sense. We're going to go through the 2 other examples here, and hopefully it'll start to kind of kick in if you haven't got a hold of this quite yet. So then we've got ethene. Ethene, I'm going to draw the Lewis structure first. Okay, here's ethene. If you don't draw the Lewis structure correctly, remember you're going to get this wrong. So what I'm going to do is I'm going to draw an s orbital over here, an s orbital over here, an s orbital right here. Oops, actually I'm going to put it right here, and then an s orbital right here. Okay, and then this is going to, I'm trying to draw it in a somewhat 3D. So what I'm doing now, the steric number on this carbon is 3, right? These carbons have 1, 2, 3 steric numbers. So I'm going to, what that means is I need 3 orbitals. So I'm going to have my S, my 3 Ps. That means I need these guys right here. So S and 2P, that's going to be sp2. And if I mix 3 orbitals, I have to get 3 orbitals out. So I'm going to get 3 sp2 orbitals. Okay, and then I've got 1 unhybridized p orbital and higher energy, so I'm going to put 1 electron in each of these. And then remember, when the steric number is 3, what do I get? I get a trigonal planar here, a trigonal planar shape. So that means it's kind of triangular shaped. So I'm going to put 1 here. Okay, that's going to be an sp2. Another one here. That's going to be an sp2. And then 1 here, like on the line. So that's going to be another sp2. Okay, and then the other carbon's exactly the same, right? So I'm just going to put this here, sp2. Another one here, oops, just like that, sp2, and then out here, sp2, okay? So now these are all sigma bonds, right? These are all each a sigma bond of some sort, and we left, what, 1 unhybridized p orbital on each of these. So I'm going to put an unhybridized p orbital here, an unhybridized p orbital here, okay? And then here's another sigma bond, right, overlapping hybridized orbitals. And then you can kind of see where this pi bond comes in, right? I have this, oops. I have this pi bond right here in the middle, right there, okay? And so it comes from this overlapping pi or p orbitals overlapping on the top and the bottom of this bond. So ultimately, hopefully, I mean, you probably saw what that structure ultimately looks like. Looks like that, right? So just remember, looking at each center atom, you remember, you kind of ignore the hydrogens. They'll always be s. They'll never hybridize. They'll just use their s orbital. But the steric number will tell you what the hybridization is and what the shape is so that you can get these accurate pictures, okay? All right, last one. Carbon dioxide, okay? Remember, draw the correct Lewis structure, so I'm going to put carbon dioxide here. Remember, we've done Lewis structures previously in this video, in this review, and in previous videos. So if figuring out this Lewis structure was hard for you, I'd refer you back to those. So this is the correct Lewis structure for carbon dioxide. Now, what I'm going to do is figure out first the hybridization on this oxygen, because it's not hydrogen. It's not going to just be an s orbital. So this has a steric number of 1, 2, 3, which means it's got an sp2 hybridization, right? So I'm going to put the center here. I'm going to put an sp2 here. Okay, and then I'm going to say that this has one of the lone pairs, and so does this one. So lone pair sp2. Okay, and then it's going to be another one right here that's going to be binding with another orbital coming from the oxygen, but the oxygen has a steric number of 1, 2. Okay, so that's going to be sp hybridized. So that's going to be an sp orbital. Okay, and this is going to create a sigma bond here. And then I'm going to put it in a linear fashion. This one was in trigonal planar fashion because it was a steric number of 3. But this one's going to be in linear fashion because it's got a steric number of 2. And then I'm going to do the same thing. Here's the other oxygen here. And then I'm going to actually draw this a little differently because you'll see why here in a second. So I'm going to draw this up here, just like this. sp2, and I'm going to pretend that that's, I'm going to have that hold one of my lone pairs and then one down here like this. Okay, and you'll see why I drew this here like this in a second. When carbon has hybridized, when it's hybridized, it's got 2 unhybridized p orbitals, right? It's got one here coming up and down, and it had one coming in and out of the page. So here's my 3D version of this. Okay, here's coming in and out of the page, just like this. Here's one of the lobes. I'll say it's the darker end of the lobe, and then there's the other lobe coming out in the back there. Now, on each oxygen also had an unhybridized orbital, unhybridized p orbital, but only one each, right? So I'm going to put one up here, like this. Okay, and then shade in this end. Let's go ahead and make this a little bigger. Okay, and this is going to be my p. Let's say this is, whoops. This is going to be my py orbital, py. Okay, because it's on the y-axis. So it's going to be overlapping with this carbon right here, on the top and on the bottom. That's one pi bond. Okay, and then this one is coming in and out of the page, right? That's going to be my pz, and this oxygen also had another unhybridized p orbital that was coming. We'll say that's coming in and out of the page because that's how it needs to orient itself in order to accommodate that pi bond. So once I do that, I get one on the top, or in the front and the back, and then I'll just label that a pi bond, and then each of these a sigma bond as well, right there. Okay, so that's kind of how it ends up looking. I'll show you the kind of prepared version before, but hopefully you can kind of see the thought process behind that, right? We figured out the steric number, it gave us the hybridization, the shape, and then we applied those to this situation here. We had to put one in the y region and one in the z region, right, coming in and out of the page. So it's kind of hard to do sometimes, but that's kind of how they'll expect you to do this on a test as well. Okay. So remember that what we've been talking about here has been valence bond theory bonding, right? This depiction here is a valence bond theory type of depiction for maybe a test question that they may ask you. But remember that there's another bonding theory that we use, which is molecular orbital theory. And this is more of a question that they would ask you in terms of molecular orbital theory. They're never going to ask you to draw a molecule and then draw the molecular orbitals on it, okay? It gets a little complicated. We actually, to get an accurate depiction, like we said before, we need a supercomputer for especially more complicated molecules. But for a question like this, when all they're going to ask is ask you to fill out a molecular orbital diagram based on what the compound is. So in this case, we have a carbon monoxide. Okay, so carbon binding to oxygen. And all that's happening is that we have a carbon and an oxygen side. And remember that each of these guys has an s orbital. Okay, I'm going to put, let's go ahead and put just an s, or the s orbital here. Okay, and then they have, 3 p's each. Okay, 1, 2, 3. And 1, 2, 3. And when they're coming together, they're combining their valence electrons. Remember, carbon has 2 in here, 2 in here. And the oxygen will have 1, 2, 3, 4 up here, 1, 2 from carbon. And then based on that, they create these different orbitals, either bonding or anti-bonding. And we'll look at, we'll review which ones are which. Okay. So now it says fill out the MO diagram for carbon monoxide and determine the following: the bond order magnetism, and then they ask us to compare that to some of the ions that could be created with carbon monoxide. So now, all we have to do then is figure out the valence electrons that carbon monoxide has. So in this case, we got 4 coming from carbon and 6 coming from oxygen, which is 10 valence electrons. So I'm going to fill in 10 valence electrons into this diagram. 1, 2, 3, 4. Now, I'm going to count this 5, 6. The reason that we do that is according to what we call Hund's rule, okay? And this is not too important right now, but it'll become important once we get into more complex stuff. And it may even determine whether something is diamagnetic or paramagnetic, okay? So like on a bus, we humans typically fill in a seat, an empty seat, before they start pairing up, okay? Same thing with electrons. Because they repel each other, they'll be as far away from each other as possible before they have to pair up, okay? So 2, 4, 5, 6, 7, 8, 9, 10, okay? So that's 10 valence electrons. And now we need to determine the bond order. Now, bond order, remember, is bonding, okay, minus anti-bonding. I'll just put anti over 2, okay? Now, bonding will always be in the non-asterisked orbital, okay? Meaning it's going to be this guy, and this guy. So in here, we've got 2, 4, or sorry, not 4, sorry, 2, and then 4, 6, 8 total valence, total bonding electrons. So I'm going to say total 8 minus 2. Okay, 2 anti-bonding orbitals because it's got this asterisk here. So let me go ahead and kind of clean this up a little bit. So now it's going to be 8 minus 2 over 2, right? Over 2. That's going to be 6 over 2, which just ends up being 3. Now, what you can do is draw the Lewis structure and see if that verifies what you're seeing. So in this case, I'm going to put carbon, triple bound, or in this case, I'll draw the structure as carbon. And then oxygen and give everybody their octet, right? And then I'm supposed to have 10 valence electrons. So I have to cancel out this guy and then make a bond out of it, right? So that's what I'll do. And then I'll do it again because we end up having to get rid of even more valence electrons to get to the 10 that we need. And in this case, we got 2, 4, 6, 8, 10. Yep, now we're at the correct valence electron count. And you can see that this is going to have, has a triple bond, right? Now, yes, there is a negative charge on this guy and a positive charge on this guy if you look at the formal charges, but they're not going to make a fourth bond because they can't expand their octets, okay? So it's just going to stay like that. But we do see the triple bond, which verifies our bond order of 3. So when you do these, you can kind of verify looking at the Lewis structure to say, hey, this has a bond order of 3. Do I expect that when I draw the Lewis structure for there to be a triple bond or, you know, a double bond if the bond order is 2 or so on and so forth, okay? Now, magnetism has to do with whether electrons are paired or unpaired. Now, in all these electrons are paired. And what do we call that? We call that diamagnetic. Diamagnetic, okay? Which means it's not going to exhibit any magnetic properties, okay? We only exhibit magnetic properties if we are paramagnetic, which would mean there's an unpaired electron somewhere, okay? So now they're asking us if we're comparing this to the ionic versions of carbon monoxides, like carbon monoxide plus or carbon monoxide minus, which ones would have the stronger bond? Or so if I look at this, I can look at the molecular orbital diagram. I'm going to change the color here. If I add, let's say I'm doing this for carbon monoxide plus. So that means I'm going to be taking away an electron, okay? Now, if I do that, that means I decrease the number of bonding electrons. So now it's going to be 7 minus 2 over 2, which is 5 over 2, which is 2.5. So the bond order went down when I created Cl plus because I took an electron out of a bonding orbital. Okay, now if I look at the same for the CO, okay, the CO plus or CO minus, I mean, that means we're adding an electron in here. So I'm going to add the electron up here. Okay, now instead of 7 minus 2, it's going to be 8 minus 3, right? Because now I've still got my 8 bonding electrons, but now I've got 1, 2, 3 anti-bonding electrons over 2. That's also 5 over 2, which is 2.5, okay? So these are both 2.5, which means both of them decrease the bond order. Now, that shows us a very important concept. If you ever add electrons into a bonding orbital, you will always increase the bond. If you ever take them out, you will decrease the bond order. If you ever add electrons into an anti-bonding orbital, you will decrease the bond order. Or if you take them out of an anti-bonding orbital, you will decrease the bond order, or you will increase the bond order, okay? So just recognize those patterns. And as long as you know how to fill in these molecular orbital diagrams and recognize which ones are which ones are bonding, which ones are anti-bonding, you should be fine as far as the test goes, okay? All right, so now they say draw the molecular orbitals. This is something that you should know how to do. And instead of just drawing them with you, I'm just going to show you a picture and show you how we got them. Okay, so here's the picture that I came up with. And what we do in order to get these, let's say we were going back to our carbon and oxygen binding together. Okay, remember carbon has an s orbital and p orbitals. Now we're not talking about hybridization in this theory necessarily. Okay, so we know that carbon and oxygen each have their respective s and p orbitals. Now when this s orbital comes together with this s orbital, we have to get two orbitals out. And what ends up happening is we create one that's in lower energy and an orbital that's in higher energy. And then we end up filling these electrons depending on how many valence electrons each one has. We do the same one with these p orbitals, right? We have a px, a py, and a pz, a px, a py, and a pz on both sides. And what they do is they create both a sigma, but I didn't discuss what this was called down here. This is a sigma s orbital, okay? And this is what it looks like. This is when we mix this with this, we get this, okay? That's one shape that you'll have to know. Or this is the anti-bonding version of it, which just means we put a node down the middle instead of combining them. And so instead of having this, we just cut it right in half, and then we end up getting these orbitals that face away from each other, out of phase. Okay. So same with p orbital, you can have at least one sigma p orbital, but you can't have more than one. But you can have multiple pi orbitals. Okay. So that'll happen when you get the two px's to come together. You'll get the sigma p over here. Okay, they kind of mix in the same way. And then with the anti-bonding for this guy, which is up here, right? We actually just end up canceling or putting a node right down this guy. And so you can see how we get this structure up here. And then with these guys, they kind of make these like hamburger/hot dog forms. We get the two nuclei here in the middle, and you can't really see it here, but they're inside here on that structure. It's just in 3D. And in order to get the anti-bonding version, we just throw a node in the middle, and that puts it into higher energy. And then this whole part right here is where you actually fill in the electrons with, and then that's how we determine the bond order and such. So mostly out of this is what you should know is what these shapes look like. Okay, what an s bonding orbital looks like, a sigma s bonding orbital looks like, what a sigma p bonding orbital looks like. What a pi p looks like, what a pi anti-bonding, a sigma pi bonding, or sigma p bonding, sorry, anti-bonding, and so on and so forth. So you should be able to recognize which ones are which based on, firstly, what the shape is, how many nodes they have, and if they look, if they're overlapping the nuclei or if they're just above it and below it, okay? So hopefully, if you want to, you're welcome to, screenshot this off the video or whatever, if this will help you study the shapes of molecular orbitals. But there will be a question on the test, and I know exactly which one it is, where they're going to have you match certain orbitals, and you're going to have to know which ones go to which, okay? Now, there are important applications of molecular orbital theory, particularly when we talk about metals, okay? And there's going to be a type of question that they're going to ask you this question. It's going to ask you to identify the molecule or the following as a metal, semi-metal, or doped semiconductor, or an insulator. Okay. To introduce this concept, I'm going to show you a diagram that helped me a lot to understand this. So, in molecular orbital theory, remember when, let's say we've got one sodium atom, the second we put two in there, we create a bonding and an anti-bonding, and then we put a third one in there, we create bonding and then an anti-bonding, bonding, anti-bonding, bonding, anti-bonding, and so on and so forth. What ends up happening is on the scale of moles, right, we end up creating this huge band of empty orbitals and a huge band of bonding orbitals, so of full orbitals, I should say. So what we end up doing is we call this bonding section the valence band, and this section here the conduction band. Okay, and now the distance between them can determine a lot about how this particular metal will conduct heat or electricity. Because let's say I excite this electron, right? Remember from photoelectric effect, let's say I have a photon that excites this guy. He can go up, and then when he comes back down, he could transfer that energy to this guy, who then gets excited up here or up here, and then comes back down, transfers that energy here, and that's how the electricity or the heat will move across. All that's happening is a bunch of electrons are just coming up and down and moving across or transferring their energy across to the next electron across from it. So that's kind of the idea behind or the concept that molecular orbital theory is trying to explain in terms of conduction of heat and electricity. So if the thing to know is that if these bands are close like this, okay, if they're overlapping, we call this a conductor, okay, a conductor. So in this case, we'd also call this a conductor. However, if there's any hint of a gap between them, such as this guy, we actually call this a semi-metal. Okay, a semi-metal or semiconductor, or more. We actually, for the test's sake, you'd call this a semiconductor. Okay, semiconductor, meaning that there's actually this energy gap. We call this E gap. Okay, and there's somewhat of an energy involved in order to excite those electrons upward, but sometimes they'll go up and they'll come back down because this gap is relatively small. So as long as you can recognize that one is a conductor and one is a semiconductor, and we can even look at this one really quick. This is the insulator. Insulator just means the energy gap is so large that there's hardly going to be any conduction at all. This is found in stuff like rubber or styrofoam, right? We like styrofoam because in our hot chocolate we don't want it to conduct heat, and so we use something that has this huge gap, energy gap between the conduction and the valence band. Okay, but now there is kind of a subgroup of semiconductors that we designate as either N or P, and I'll kind of illustrate what each of those means here in a second. So N, when we dope something, first of all, when we dope something, what we're trying to do is decrease this gap. Okay, we're trying to decrease the energy gap so that we can actually conduct things easier using the semiconductor. And actually, semiconductors are heavily used in technology. Like our phones have a lot of semiconductors, so these are really important. They actually do a lot of things for us. But doping them can actually help us use them in more effective ways. So both doping both types of doping have the same effect. They decrease the energy gap. However, N doping would be when we're adding negative. So N means negative and P means positive. Negative means we're adding electrons to it, which means we're adding full orbitals to them. So here I'm adding this here to that. That's that little gray bar there. That's right next to the conduction band. That makes this gap right here instead of right here. Okay, so it has significantly decreased this gap. And these are just filled orbitals here. These are just filled valence orbitals, okay? And so it makes it easier to excite these guys to go up here and come back down here to conduct the electricity or the heat or whatever it may be. So this is the N dope. This is the N dope because we're using electrons, okay, which are negatively charged. That's the N right there. To decrease the band gap, and you'll see that gap there, the doping, the bar, way up close to the conduction band. So kind of confusing because you may think that the gray is associated with empty antibonding orbitals, but in this case it's not. It's actually just filled valence orbitals, but they're just higher, okay? Okay, and letter A here, just by default, you could probably guess that this is going to be the p dope. Okay, this is the p dope because what we're doing is we're adding empty antibonding orbitals. Okay, we're adding these guys here. Okay, so that means the orbitals that are filled here can jump up to these now empty orbitals up here and then get excited back down instead of having to go all the way up here and then come back down to cross that energy gap. Now they just have to go up this distance, okay? And so doping kind of helps us to decrease that energy gap. And you can either have the N dope, where we fill it with extra electrons, and here we do that with the P dope by adding empty orbitals. Now, some people may ask, well, how would you dope? Well, all we do is we create sort of like alloys. Alloys are just like mixtures of metals. And let's say I have copper. If I dope it with, let's say, gallium, gallium is in the third group on the periodic table. So let me put 3. Okay, so that means it actually has less than the number of valence electrons that carbon would have, or copper would have, and I would expect that to then add. That would be a good p doper, because what we're doing is we're adding a bunch of orbitals that aren't filled. Right, we have these. We only have 3 valence electrons. And so there's a bunch of other empty orbitals that are in there, like the empty p orbitals, that I can add to then p dope, okay? Or if I was to, let's say I was to dope with something like sulfur, okay? Or not sulfur because that's a nonmetal, but let's say, I don't know, like germanium. I think germanium is in the 5th group. I'm not looking at the periodic table right now, but let's say it was in the 5th group, okay? That means it has a lot of extra valence electrons. And so That's a good N doper. So typically when we're looking at what metals will make good N or P dopers, you'll have to look at the number of valence electrons. If it's less than 4, it's likely going to be a P doper, and if it's greater than 4 or like greater than 5, it's probably going to be an N doper. Okay, meaning it's adding valence electrons. Now I'm not sure if on your test you'll actually have to know something like that. But in case you were wondering why, how we get one or the other, I thought I'd just just mention it to you. All right, that'll finish it up for this exam 2 review. I hope this was helpful. Like I said, this test may or may not be accurate for future classes, but as far as fall 2021 goes, it is pretty accurate as far as the test content goes. If you're using this at any time in the future, I have to give the disclaimer that I'm not sure if all this material will be on the test, or if it's even cumulative or covers everything that you need to know. But either way, good luck. Best of luck to you. In the 7 semesters that I was a TA, I found that there were 3 really helpful things for the tests. Reviewing all the problem sets. And now by reviewing problem sets, what I'm really talking about is like not just going over them briefly and saying like, yeah, I know how to do that. Yeah, I know how to do that. I'm talking about going through each problem set, covering up your answer and knowing what the answer would be before you uncover it. Like knowing it to that extent, maybe not the math part, but as long as you know how to set it up before you can uncover your hands, that's totally fine. Like I'm just talking about making sure that you know this stuff backwards and forwards from the problem sets. Okay, the problem sets were designed really well, I think, because they kind of match, not necessarily the caliber. The caliber is definitely higher in the test, but it definitely teaches you the principles well. So I would say definitely review the problem sets. Go to a TA review if they hold one for you. I've heard that sometimes that TAs won't hold one. So actually, that's actually kind of what was the impetus for making this video. Was I heard that there was a demand for a review. So I've created this, but I don't make this the only thing that you watch. I would say if there's a TA review available to you, definitely utilize that because especially because TAs are used sometimes on the test, so they'll know exactly what you'll be tested on and what you won't be tested on. So they'll definitely have more accurate information pertaining to your test. And then lastly, take a practice exam that's available to you. Some of the practice exams I've noticed that Chem 105 tends to use are sometimes a little outdated. They'll have information on the tests there that you actually won't need to know for the tests. But either way, it definitely matches the caliber of the test that you'll take. So use it not only just as a gauge of where you're at, but also use it as a time to really practice your test taking strategy. So take it like a real test. And then since at least as far as fall 2021 goes, tests are timed. So I would definitely utilize it to figure out your timing and make sure you do that okay. And also just to make sure that you understand the content from that practice exam. But best of luck to you. And if you do end up needing extra help, I am available. In the link of the description, we'll have a sign up to come see me to have either one-on-one tutoring, or you can have groups up to 4 people in one session. So I would invite you to use that if you feel like that would be helpful to you. And best of all, good luck to you guys.